Welcome to this video on householder transformations. So householder transformations are a type of orthogonal matrices. The matrix corresponding to the transformation is an orthogonal matrix, and we can use it to create zeros in a matrix. So what we will do is, working on a general matrix A, we will use householder transformations to convert it to upper triangular form. And as such, we'll manage to find a QR decomposition of a matrix. There are more applications, but the example that I will give, so we'll sketch the method and then do a numerical example or an example by hand. And in that example, I will show you how we can use them to get a matrix to upper triangular form. So let's look at a little outlook of the presentation. First, I will define a householder transformation. What is it? Then I will use an interpretation as a mapping that will help understand what it actually does and how you can choose householder transformations to do what you want, basically to transform one vector into another vector. And then I will use it to transform a matrix, and I will do an example, and I'll give a short summary of the presentation. So first of all, the definition. So if you take a non-zero vector x, and if you form this matrix here, so H is the identity matrix minus 2 times x, x transpose, x, that is a householder transformation. So look carefully here. So x is a vector, a column vector that is, which means that if you do x times x transpose, you build an n times n matrix. And here in the denominator we have x transpose x, that is a number. So that is basically the length of x squared, the 2 norm. Now, there are two claims here. The first one is that this matrix is symmetric, and that is very easy to verify, because if we do H transpose, well, that is identity minus 2x x transpose divided by x transpose x transpose. You can move the transpose to the individual terms. So we have identity transpose, which is just the identity, but I write it there anyway, minus 2, and then we have x transpose, and then the transpose divided, and this is just a number, so the transpose doesn't influence that. So this is the identity matrix minus 2, and up here in the numerator we get, if you do the transpose to the individual factors, they change order. So we get x transpose transpose, which is just x, and here we get x transpose, and in the denominator we just copy that, x transpose x, and you see that this is precisely the definition of H. So apparently H is indeed symmetric. Okay? Next, it is orthogonal. So what do we need to check to see if a matrix is orthogonal? Well, the columns form an orthonormal system. We have seen that before. But the easiest way is to verify that the transpose of H is the inverse. So what we need to show this is that H transpose times H equals the identity matrix. So let's try and see if we can do that. So we have just seen it's symmetric, so this is simply H squared. So apparently if you apply H twice, you get back where you started from. If you start with the vector H, you apply H. You start with the vector X, you apply H, and you apply H again, then you're back where you started. You find your X back. So let's see how this works. I am just going to do identity minus 2 x transpose x times, well, the same thing, right? So I minus 2 x transpose x. So let's multiply and give me a little space here. So identity times identity gives me identity matrix. Identity times that one gives me minus 2, and here I'm going to find another one. So in total we find minus 4 x transpose over x transpose x. And then the last one, if we multiply minus 2x x transpose, etc. with itself, what we find is plus 4, and then we get x transpose x transpose over x transpose x squared. And now, one of the most important things if you work with all these vectors and inner products and so on is to recognize inner products. So if you look here in the numerator, you see that we have here in between x transpose x, and that's just a number. So this I can put that in front of the whole product of 4 vectors. And that means that basically what I can do is say, well, if I take this one, let's do that in a different color, sorry. If I take this number here, you see that in the denominator it is squared, so I can divide this out if I make this into a 1. And then what we have is identity minus 4x x transpose x plus 4. And basically what we have left here, so in the numerator we still have x transpose over, here we had a square, so now it's x transpose x, and you see that minus 4 plus 4, it drops out, and we have the identity matrix. So this concludes the proof that H is an orthogonal matrix. Now, this is playing a little bit with formulas and it doesn't give a lot of insight yet. So let's look at the interpretation as a mapping. So what happens if I take a vector x and I apply such an H matrix? What is going to happen there? So what I do here is I pick any vector y in Rn, and I am going to compute H times y. But here I will already show you that in principle you do not form the H matrix. Because we have seen on the previous slide that, well, this is the definition here. But from the definition you can compute this product a bit cheaper. Because, well, identity times y, that gives me just a y here. And then the second term, if I multiply that with y, this is what you get. And again, look at the product here. And note that in the numerator, we have this x transpose y, which is just a number. This is just an inner product of the two vectors x and y. So I can write that in front of the vector x. And apparently, I can compute what H does to a vector y by computing this. So I take the vector y itself, I compute an inner product with x, and then I subtract these two vectors, and that gives me hy. Having this form, I can make a couple of specific choices. So let's do that. So first, I'm going to see what happens if I would take y equal to x. Well, just plugging that in, we see that we have this expression here, but that simplifies a lot because x transpose x over x transpose x, that's just 1. So we get x minus 2x. So apparently we have minus x. So if you start with this very specific vector x that our Hausdorff transformation follows from, is based on, is defined by, then the image of x is going to be minus x. So if you think of a vector, you find the same vector but pointing in the other way. Okay. Now, another specific choice that you could make is that we pick a y that is orthogonal to x. So they make a 90-degree angle, and that means that their inner product is 0. So if you do that, well, it means that this term here is going to change, going to vanish, going to be 0. So then we have that H applied to such a vector is the vector itself. Now I can make a lot of choices for vectors that are orthogonal to x, because we have this one vector x, and then there is a whole plane of vectors. So if I draw a plane that makes a 90-degree angle to this vector, then all the vectors in that plane have this property. So if I combine that, so if I look at this space or plane V, so that's X orthoplement. You may have seen the definition before, but this is basically what it is. All the vectors that are orthogonal to X. Then basically what we have is this. If I plot it in 3D and then the plane would be 2D, then V is a plane. X is a normal to the plane, makes a 90-degree angle. And what you see is if I take h of x, I find minus x. So basically x is being mirrored in the plane, and every vector y that is in the plane stays where it is. So apparently the mapping interpretation, or geometrical interpretation if you like, is that h is a reflection in this plane. It just mirrors in the plane V. So h is a reflection in the hyperplane. In general, it's a hyperplane. In 3D, it would be a normal plane, but it mirrors vectors in V. So that is interesting. Now, what I would like to do is use these to get a matrix to upper triangular form. So that's my goal now. And it is nice to use Householder transformations because they are orthogonal transformations, and orthogonal transformations are nice to work with numerically, because they preserve length, as we have seen. If you take a vector and you apply an orthogonal mapping, orthogonal matrix, then the length doesn't change. You also see that in this picture, right? Because if you just mirror, then the length of the vector doesn't change. So x and its image minus x have the same length. Y and its image, which is y again, has the same length. So I would like to use them to transform a matrix to upper triangular form. So my Q here is going to consist of a number of Householder transformations, and my R here is going to be upper triangular. And the idea here is to do that column by column. So if you have a general matrix A and all the stars, they are non-zero entries, I am going to use one Householder transformation to create zeros under the diagonal. So I'm just going to look at the first column here, and I'm going to change it in such a way that it has zeros below the main diagonal. Next, I'm going to apply a second one to the second column. So this column I am going to transform into this here, and then I have upper triangular form. So if you call what we are left with here, if you call that capital R, then you have an upper triangular matrix. You have found it by using H2 and H1. Now the inverses of these individual matrices are H2 transpose, and H2 is symmetric, so H2 itself, and H1 transpose. So you can write A as H1 transpose, H2 transpose times R, and it's symmetric. I didn't use that here. We define Q as this product, and then Q is an orthogonal matrix, and we have A is Q times R. So this is how you can do that if you know how to choose these matrices. So basically what we would like to have now is some way to get one vector, so for instance this first column, into another one that has zeros. So how can you do that? Well, what I'm going to show you now is the following. So I'm going to say, well, suppose that you take two vectors, u and v. Then I would like to know how I should choose x to find the Householder transformation, such that so the Householder transformation maps u to v. So h u should equal v. That is my goal. I want to find x, which defines h, that has this property. There is one thing that you should take into mind. This u and v, you cannot choose them completely freely because h is going to be an orthogonal transformation. It preserves length. So I can only find such an H matrix if u and v have the same length. So here's a claim. The claim is that if you have such vectors with equal length, then you should pick u minus v and then the corresponding H matrix does what you would like it to do. So let's see how we can prove that, and I'm going to need a bit more space than I have here on this slide. So let me also add a slide here. So what do we have? We have two vectors, u and v. So we have u, v in Rn. They are given. The length of u in the 2 norm equals the length of v in the 2 norm. So that means the inner product of u with itself is the inner product of v with itself. Like this. And the theorem tells us that if we pick u minus v and then the corresponding H matrix, identity minus 2x, x transpose x, this accomplishes what we would like it to do. So let's see how that works. So I am going to start with H times the u vector, and I need to show that it equals v. So we have this equals u minus 2x, x transpose u over x transpose x. Which is u minus 2. And then here we get let's do it slowly. X transpose u, x transpose x times u. So what I did here is I recognized that this is the inner product of x and u, which is a number, and I can write that in front of the vector u. So here, sorry, I did it incorrectly. This should of course be x. Sorry about that. So I write this in front of the x, and then we have this expression. And now I'm going to plug in our choice for x. So we have, we have u minus 2, and here we made the choice u minus v transpose u over u minus v transpose u minus v times u minus v. Okay. And this is the same as u minus 2. And I can write the numerator as u transpose u minus v transpose u. And below here I have u transpose u minus u transpose v minus v transpose u plus v transpose v times u minus v. Now this still looks a bit ugly, but there is two things we should note. First of all, here I have u transpose u and here I have v transpose v. They are equal, as we have seen here, up here. So I can write this together as 2u transpose u, and also, let's pick green, these two are both the inner product of u and v, so they are the same, and I can write them as minus 2v transpose u. Okay, so let's see what we have now found. So I'm going to copy what we have to the next slide. So what we found here now is that h applied to u equals u minus 2. In the numerator, I just copy, we had u transpose u minus v transpose u. In the denominator, we have apparently 2u transpose u minus 2v transpose u, and the whole thing times u minus v. Now, if you look carefully at the quotient that we have here, so this thing here, then you see that the denominator is twice the numerator. So apparently, I can write this as u minus 2, and this is a very complicated way to write a half, times u minus v. So we have u minus u, it drops out, and we find v. So indeed, this transformation does what we would like it to do. So that is great to know, because now we have the correct transformation to, if you give me two vectors that have equal length, I can find the Hausdorff transformation that maps u to v. So how can we use that? So assume that we have a matrix, A, it's square. I'm going to write it in terms of its columns. So the columns of the matrix are A1 up to AN. And in the first step, I would like to transform this first column here into something that has zeros below the diagonal. So some number at the 1, 1 position of the matrix, or the first position of this vector v here, which I call alpha, and the rest is going to be zeros. So you can write it as alpha times E1, and E1 is then the vector 1, 0, 0, 0. Now, u and v must have the same length. So what we find is that the absolute value of this alpha, that's the length of v, should equal the 2 norm of the first column, which means that we can pick alpha to be plus or minus alpha itself, so not the absolute value, can be plus or minus the 2 norm of the first column. And then the corresponding v is plus or minus this alpha times E1. Now I have my u and v. For v I have two choices. And the corresponding h1, so h1, because it works on the first column, is, well, the Hausdorff transformation that is being induced, if you like, by u minus v, x is u minus v. And since there is a minus sign here, I get minus plus alpha E1. And you could choose either of them, and the standard choice is to avoid cancellation. So basically, if A1 has a non-negative first entry, we're going to take so that it's plus here, and if A11 is negative, then we take the minus sign. So then they have the same sign and you will not have cancellation. So just as a reminder, cancellation means that you have two equal numbers and you subtract them. And on a computer, you may lose digits, significant digit if you do so. So we try to avoid that. So after we have done this first step, we have created zeros here in the first column. But we still have the rest of the matrix. So this here, the n-1 times n-1 lower right block, still needs work. But it goes the same. So what we do, we call this thing that we still need to work on, we call that capital B. We write capital B in terms of its columns. Then we transform the first column just like we did on the previous slide in beta E1, and beta, the value, is the length of this column here. And then we get an x hat vector, which is one less, so in Rn minus 1. And that has a corresponding Householder transformation, but that Householder transformation is smaller in size because it works on n minus 1 times n minus 1 matrix. And we can extend that to a full H2, to a full matrix, if we just add a 0 at the top left and zeros in the first row, zeros in the first column. And if you apply that to the original matrix, so you do H2 times H1 times A, then you also create zeros here, and you keep the zeros in the first column, so you don't spoil them, you don't destroy them. And then we have an n minus 2 times n minus 2 lower right block, which we could call C, and so on. So what you will see is that you can transform your matrix column by column into an upper triangular matrix. And in general, you may be lucky that you already get zeros, but in general, you will need n minus 1 Householder transformations, because the last column, you don't need to create zeros there. But for the first n minus 1 columns, you may need a Householder transformation. And then the matrix itself is this, and you can call the product of these H matrices Q, and the resulting upper triangular matrix you can call capital R. So that is the general outline how it works. Hopefully that was a bit clear. I'm going to do a numerical example now to help you understand how this works. So I'm going to look at a 3 by 3 matrix, and I am going to solve a linear system. So I'm going to solve the system AX equals B, where B is this vector, and I will do that using the QR decomposition. So first use Householder to find the QR decomposition, and then use the QR decomposition to solve the linear system. As you can probably imagine, we are working with orthogonal matrices here all the time, which means that the columns are vectors that have length 1 in the 2 norm. There are going to be a lot of square roots in here. So maybe for a computer, orthogonal matrices are nice to work with. If you do computations by hand, they are not so nice because you have to normalize them all the time. You have to give vectors length 1 all the time, and that causes a lot of square roots to occur. So by hand, it's a bit of a mess. So let's see for the example. So what I'm going to do is I am going to write my matrix here. So here the matrix, I am going to write that as A is A1, A2, A3. So A1 is the first column, which is 1, 2, 2. And I would like to transform that into alpha 0, 0 using some Householder transformation H1. So for alpha, the two vectors, so this vector 1, 2, 2 and this new vector should have the same length, which means that alpha can be plus or minus the square root of 1 plus 4 plus 4, square root of 9. So alpha is plus or minus 3. To get this to work, I need the Householder transformation H1, which is identity matrix minus 2 x1 x1 transpose over x1 transpose x1, and x1 we have seen in the theorem U minus V, where U is your original, so that's the 1, 2, 2, and you have minus alpha 0, 0. So what we get is 1, 2, 2 minus, and alpha was plus or minus 3, 0, 0. And now the choice that we make, since 1 is positive, we're going to choose the plus sign here. So we are going to choose so both would work, but we're going to choose 1 plus 3, so we're going to choose 4, 2, 2. So we are going to map, we are going to use x1, this vector. So choose x1 equals 4, 2, 2. So that gives us the first Hausdorff transformation. So we have apparently h1 with this choice for x1 should create zeros in the first column. So if I apply this to my matrix A, then this 2 and this 2 is going to disappear and is going to be a 0. So let's see if that indeed works out. So I need some more space for that. So what we have is that h1 applied to the A matrix is h1 applied to the first column, h1 applied to a2, and h1 applied to a3. h1, a1 by construction is minus 3, 0, 0, because I chose the x1 to map the first column to this vector. Now to compute, you can also check that. So if you would compute it by, you could also say, well, h1, a1, that is the same as a1 minus 2 x1 transpose x1 a1 a1 is the vector 1, 2, 2. x1 is the vector 4, 2, 2. So we see that x1 transpose x1 is 16 plus 4 plus 4 equals 24. And here we get the inner product of x1 with a1. So there we get x1 transpose a1 is 4 plus 4 plus 4 is 12. Yep, that's correct. So we get that h1 a1 equals 1, 2, 2 minus 2 times, and then we get 12 over 24 times a1, x1, and x1 is 4, 2, 2. So indeed, this here is 1, and we get 1 minus 4 equals minus 3, and here we get 0, 0. So indeed it works out. And what you see is it's quite a bit of work by hand. We also need to do that for the second and for the third column. So let's also do the second column. So what we get there is that h1 a2 equals a2 minus 2, and you can probably imagine that we get x1 transpose a2 over x1 transpose x1 times x1. And if you compute that, so you have to compute this inner product, the other one, so you have to compute this inner product. And if you do that, you would hopefully find minus 66. You can do that by hand. This one we already computed here. And if you compute this number, I did it on a bit of scratch paper, so I'm immediately going to write this down. But the vector that you would get is 15 minus 9 and 12. So I trust you can do that. If you have troubles, let me know. And similarly, H1A3 is going to hopefully result in minus 4, 3, minus 1. So what we have found after this first step, so as a kind of in-between conclusion, is that H1 applied to A is minus 3, 0, 0 for the first column. So that was our goal. We wanted to create zeros below the diagonal. Here we have 15, minus 9 and 12. And minus 4, 3 and minus 1. And then in our next step, we have to consider this 2 by 2 block. So in the previous slides, I called this B. And the next step is to transform minus 9, 12 using H2 hat. I put the hat there because it's a 2 by 2 matrix, to some beta 0. Now, H2 hat is a Hausdorff transformation. It preserves length. So we need that beta equals plus or minus the square root of minus 9 squared is 81 plus 12 squared, 144. And you see that I try to get more or less nice numbers here, because this equals plus or minus the square root of 225, which is plus or minus 15. So now we know how to choose the second Hausdorff transformation. So what I would like to choose now is H2 hat is identity minus 2 x2 hat x2 hat transpose over x2 hat transpose x2 hat. And this x2 hat, well, it's u minus v. U is minus 9, 12 minus v, that is beta 0. Plus or minus 15, 0. So we choose. So now we have minus 9 and we would like to subtract 15. So we want minus 15 here. So we are going to choose x2 hat is minus 9 minus 15, so that these signs agree. 12, which is minus 24 and 12. Now, by construction, H2 hat applied to minus 9, 12 is plus 15, 0. H2 hat and then applied to, go back to the previous slide. So we are working now on this B matrix. So we also need to know what happens to this 3 minus 1 vector. And if you compute it, so 3 minus 1, you hopefully find that that is going to be 1/5 times minus 13 and 9. So what we have now found is, so if we introduce a matrix H2 like this, so the smaller Hausdorff transformation, but then back to the original size by using a bit of the identity matrix. So then H2 H1A is equal to, well, the first column doesn't change. The first entry of the second column also. The second becomes 15, 0. And then here we have minus 4, that doesn't change. And this is the minus 13 over 5 and 9 over 5 that we have just found. So with these two Hausdorff transformations, we have found an upper triangular matrix. And this bit here is Q transpose, so the orthogonal matrix. That is the bit on finding the QR decomposition. Now, the original question was also to solve a linear system AX equals B. So what we do now is that we say, well, that has the same solution as H2 H1 AX equals H2 H1 B. So we still need to compute this thing here, but on the left the system changes to Rx equals H2 H1 B. Now if you compute those things, I did that on a bit of paper as I told you, then you will find that H1 applied to B should equal 21 minus 9, 21. And if you compute H2 H1 B, hopefully you are going to find, with a bit of work, 21 111 over 5 and 27 over 5. So then the last bit that we need to do, and that's going to be the last bit of this example too, is that we have now to solve R times X equals H2 H1 B. The R matrix, the upper triangular one, is minus 3, 15 minus 4, 0, 15 minus 13 over 5, 0, 0, 9 over 5, times x1, x2, x3, that's the solution of the linear system we're looking for, 21, 111 over 5, 27 over 5. So since this is an upper triangular matrix, we can solve this using backward substitution. Which is just a fancy name of saying, well, start with the last equation, 9 over 5, x3 is 27 over 5. So apparently x3 equals 3. Next, move to the second equation. So the second equation tells us that 15 x2 minus 13 over 5x3 equals 111 over 5. Plug in the value for x3 that we just found, which is 3, and then solve for x2. And if you do that, you should find x2 equal to 2. And then finally we go to the last equation, which is the top equation, minus 3x1 plus 15x2 minus 4x3 equals 21. And then if you plug in the values for x2 and x3 that we already found, you should hopefully find x1 equals minus 1. So quite a bit of work, but this concludes the example. So this shows us how we can find a QR decomposition and how we can find the QR decomposition to solve the linear system. So let's wrap up this video. What have we seen? We have seen how you can use Hausdorff transformations to map one given vector to another one, provided they have the same length, that's a requirement. How you can compute the QR decomposition using Hausdorff transformations, and then how you can solve a linear system using the found QR decomposition. And that concludes this video. I hope to see you in the next one.